Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 2. In this video, we're going to look at the addition and multiplication properties of equality. The objectives in this section are to define linear equations and use the addition property of equality to solve linear equations. Next, we'll use the multiplication property of equality to solve linear equations. And then we will use both properties of equality to solve linear equations. And finally, we will write word phrases as algebraic expressions. You may remember we did a little bit of that in the last section. In this section, we're addressing student learning outcome B. And the important part of that for this section is solve linear equations. All the other words you see there, we will do in other sections, other chapters. All right, so let's start by talking about what is a linear equation. A linear equation is an equation that can be written in the form ax plus b equals c, where a, b, and c are real numbers and a does not equal 0. So already this looks kind of like alphabet soup, but in a given problem, A, B, and C will be specific given numbers. So for example, 2x plus 3 equals 4. A linear equation will always have one variable, in this case, x, and that variable will be raised to the first power only. So the goal in solving a linear equation is to transform the equation ax plus b equals c in whatever form it's in into the equation x equals a number using operations that produce equivalent equations, which means equations with the same solution. So we're going to use two properties to make that transformation. The first one is called the addition property of equality. And what it says officially is that if A, B, and C are real numbers, then the two equations, A equals B and A plus C equals B plus C, those two equations are equivalent. They have the same solution. So here's a GIF that I found about 100 years ago. You can tell by those neat 8-bit graphics there that I think does a good job of illustrating the addition property of equality. They're starting with the equation x plus 10 equals 15, and they're showing that by subtracting 10 on both sides, you get the solution of the equation, which is x equals 5. This thing that all of the balls are sitting on, I think, is supposed to be a balance scale. Again, those great 8-bit graphics. All right, so what this property says in English is that you can add or subtract the same number on both sides of an equation without changing the solution of the equation. So here is the first batch of examples we're going to go over. I will switch over to the tablet. And that gives us our first example, y minus 9 equals 1. So what you need to do is look at what is being done to the variable and do the opposite of that in order to get the variable by itself, okay? So in this case, the variable is having 9 subtracted from it. The opposite of subtract 9 is add 9. So I'm going to add 9 to both sides of the equation. And that is going to give me y on this side equals 1 plus 9 is 10. Okay. Now, one thing that I strongly recommend doing whenever you solve any kind of equation is to do a check. And how you do the check is to take the original equation, y minus 9 equals 1, and see if that equation is true when you substitute what you think the solution is. We think the solution is 10. So the question right now is 10 minus 9 equal to 1? Well, yes, it is. 10 minus 9 is 1. Woo! All right. So the solution of this equation is 10. That is officially the correct way to write it. If you were writing this on paper for me and you wrote y equals 10, that would be okay. All right, but technically it's a number 10 in a pair of curly braces. Okay, next we have t minus 9 and 2/10 equals negative 6 and 8/10. Very, very similar to the last example, except that there are decimals involved. The opposite of subtract 9 and 2/10 is add 9 and 2/10. So that's what I'm going to do. I'm going to add 9 and 2/10 to both sides. On the left-hand side, those two things drop out. And on the right-hand side, I have negative 6 and 8/10 plus 9 and 2/10, which is 2 and 4/10. Okay, so I think what I'm going to do to save a little time is maybe in about every other problem, I'll do the check. I just don't want you to forget that it's a good thing to do. But if I do it in every single problem, then the video is going to be a lot longer. All right. So I'll do the check in this problem. We have 9x plus 5 and 5/10 equals 10x. Now this one's a little more complicated. We have x's on both sides. So we're going to develop a process for this in the next section. But in the meantime, what I'll tell you is that when you have x's on both sides of the equation, what you have to do is use the addition property of equality to get x on one side only. So you actually have two choices here. You could subtract 9x on both sides of the equation, or you could subtract 10x on both sides of the equation. In this case, I am going to subtract 9x on both sides. I have a couple of reasons for wanting to do it that way, which I will not bore you with. Just know that in general, it doesn't matter. I could have done minus 10x on both sides. That's going to drop out on this side. I'm going to have 5 and 5/10. Oh, well, here's one of the reasons I chose to do it the way I did, because I saw that the right-hand side was going to be 10x minus 9x, which is 1x. So that's just x. And that is my solution. As promised, I am going to do the check because I didn't do it in the last problem. So remember to always check it in the original equation. I'm going to write 9 times blank plus 5 and 5/10 equals 10 times blank. And I think that when I put a 5 and 5/10 in the blank, that is going to make the equation true. So let's see. 9 times 5 and 5/10 is 49 and 5/10 plus 5 and 5/10 comes out to 55. On the other side, 10 times 5 and 5/10 is also 55. Woohoo! So that checks out. All right, last example in this batch, 7y plus 2 equals 2y plus 4y plus 2. So again, a slightly more complicated example. I have y's all over the place. In particular, I notice that I have two y terms on the same side of the equation. So the very first thing I want to do is combine those. I'm going to leave this side alone for right now, 7y plus 2, and then 2y plus 4y is 6y. All right. So now it looks a little bit like the last example. I need to get a y term on only one side of the equation. So this time the way I'm going to do that is I'm going to subtract 6y on both sides. And that is going to make the 6y terms drop out on this side. And on the other side, 7y minus 6y is 1y, which is y. Y plus 2 equals 2. So we're almost there. The last step is I have to get y by itself. So now the equation looks a little like the first example. If y is having 2 added to it, the way to undo that is with minus 2. So I'm going to do minus 2 here, minus 2 here. These are going to drop out. Now, one of my things that I like to say is once an equation, always an equation. If you start with an equation, in every single step, you need to get another equation. So what you have to remember to do in this particular problem is to keep the equal sign, and on the other side, write 0. 2 minus 2 is 0. Okay. All right. So the solution, and since I did the check in the last example, I'll leave it for you in this one, is 0. The number 0 is the only number that will make that equation true. All right, back to the presentation. So next, we're going to talk about the multiplication property of equality. Officially, what that says is that if A, B, and C are real numbers and C does not equal 0, then these two equations, A equals B and A times C equals B times C, those two equations are equivalent. They have the same solution. All right. Yeah, this, I couldn't find a moving GIF when I went to find this one 100 years ago. But the idea is, let me see if I can write on this. It represents the equation 3x equals 3 times 8. In other words, 3x equals 24. So the idea is that if you divided this side of the equation by 3, you would have only one of these mystery boxes left. And if you divided this side of the equation by 3, you would only have one of these stacks of little boxes left. So on this side, you would have one mystery box. And on this side, you would have one stack of 8 little boxes, excuse me, which represents the equation x equals 8. Okay, by dividing both sides by 3. All right, so what this property says in English, let me get rid of my scribble here and get my mouse back. Uh-oh, this happens a lot of the time. Okay, got it. In English, this says that you can multiply or divide the same number as long as it's not 0 on both sides of an equation without changing the solution of the equation. You might be wondering, well, why can't you multiply or divide by 0? Well, you're never allowed to divide by 0, right? That's an undefined operation. But even multiplying both sides of an equation by 0 does things that we don't want to do. And I will get into details in a later section because this actually comes up. You have to be careful sometimes that you're not accidentally multiplying both sides by 0. All right, next batch of examples are right here. There's just 3 of them. So let's switch over back to the tablet. And the first example in this batch is negative 7x equals negative 49. What's being done to the x is it's being multiplied by negative 7. The opposite of multiplying by negative 7 is divide negative 7. So that will cancel out the times negative 7, and it will leave me with x equals negative 49 divided by negative 7 is 7. And I think I'm due for a check. So let's take the original equation, negative 7x equals negative 49. I'm hoping that's still true if I put a 7 in the blank. And you can see that that is true, right? Because -7 times 7 is -49. Woohoo! All right, so the solution is 7. Next example, -y plus 4y equals 33. So whenever you have more than one y term on the same side of the equation, you want to combine those. So remember, negative y or opposite y means the same thing as -1y. -1 plus 4 is 3. So this combines into 3y equals 33. The opposite of times 3 is divide 3. So we're going to divide both sides by 3. And that is going to give me a y on the left side. And 33 divided by 3 is 11. The solution of this equation is 11. And that check is left for you. Last example in this batch, 3/4 n equals -15. So I'm going to show you a shortcut that you can use anytime your variable is being multiplied by a fraction. And that shortcut is to multiply both sides of the equation by the reciprocal of that fraction, which would be 4/3. Remember to do it to both sides. The reason that we use the reciprocal is because, remember, we're trying to get the variable by itself, and any fraction times its reciprocal equals 1, because in this case, the 4's cancel, the 3's cancel. So that just leaves me n. Now I just have to figure out what this side comes out to. So I'll sneak a 1 under there. 3 and 15 have a common factor 3. 3 divided by 3 is 1. 15 divided by 3 is 5. Don't forget there's a negative sign there. So that right-hand side comes out to -5 times 4, which is -20. All right, this one I will check. Original equation was 3/4 n equals -15. I want to know if that's true when I put a -20 in the blank. So drop my fence down, put a question mark. I'm going to sneak a 1 under this -20. 4 and 20 have a common factor 4. 4 divided by 4 is 1. 20 divided by 4 is 5. 3 times -5 is -15. Woohoo! So that equation does check. And the solution of this equation is -20. I think I forgot to write this sentence in the last example. That's okay. All right, back to the presentation. Next thing we're going to talk about is using both properties. If I can get this, there we go. All right, using both properties. So here are the examples I have for that. I think, yes, there are 4 of them. So back to the tablet. And let me get on the right screen here. All right, first example, 3x minus 1 equals 26. So a lot of times, students who are taking algebra for the very first time get a little confused about what to do first, right? We want to get that x by itself. So how did the x turn into a 3x minus 1 to begin with? Somebody multiplied it by 3 and then subtracted 1. We need to undo those things in the opposite order. So in other words, somebody took an x, multiplied it by 3, and then subtracted 1. We need to undo those things in the opposite order. It's like in the morning, you put on your socks and then you put on your shoes. When you come home, what do you take off first? You take off your shoes. So the first thing we need to do here is add 1. So let's do that. That plus 1 will undo this minus 1, and it will leave me 3x equals 27. And then the next thing I need to do to undo times 3 is divide 3. So we're going to divide both sides by 3, and that is going to give me x equals 9. All right, I think I'll check this one because it's kind of a new, well, it's a new kind of equation. Original equation, 3x minus 1 equals 26. If I put a 9 in that blank, I think you can see it's going to work out. 3 times 9 is 27. 27 minus 1 is 26. Woohoo! The solution is 9. All right. Next, -3n minus 1/3 equals 8/3. When we get to the next section, I'm going to have some specific advice about dealing with equations that have fractions in them. But in this case, we can do this one just like we did the last one. All right, so somebody took this n and multiplied it by -3, and then they subtracted 1/3. So the first thing we have to do is add 1/3. So let's do that first. Add 1/3 to both sides. That's going to get rid of that, and it's going to leave me -3n equals 8/3 plus 1/3 is how many thirds? It's 9/3, right? Now we're in luck. 9/3 happens to simplify to 3. Okay. All right, but we're trying to get n by itself. So the next thing we need to undo is times -3. And you do that by dividing -3. So we'll divide both sides by -3. And that is going to give us n equals -1. And because I checked the last one, I will skip the check on this one. Last example. 19 equals 4/10 x minus 9/10 x minus 6. So once again, we have a pair of like terms on the same side of the equation. So the first thing we have to do is combine those. 4/10 minus 9/10 is -5/10. See, this is one reason why I suggest so strongly that you do the check at the end. It would be a really easy mistake to say 5/10 and forget the negative sign. If you made that mistake, it would come out in the check. You would see that the check didn't work out. You would go back and hopefully you would find your mistake. All right. So next we're going to undo the -6. So let's add 6 to both sides. So let's get rid of that. And that's going to give me 25 equals -5/10 x. And finally, how do you undo times -5/10? With divide -5/10. All right, so on this side we have x, And on the other side, feel free to use your calculator here. 25 divided by -5/10 is -50. And I guess I'm due to check this one, huh? Take a little sip of my drink here. Okay, so we think the solution is -50. Let's see, can I fit the check in this space over here? Hopefully. Okay, so check. 19 equals 4/10 x minus 9/10 x minus 6. Okay, kind of a tight squeeze. We want to know if that's true. If I stick a -50 here, question mark, put down the fence. All right, 4/10 times -50 is -20. 9/10 times, or minus 9/10 times -50, that's going to turn into plus 45 minus 6. -20 plus 45 is 25. 25 minus 6 is 19. Woohoo! All right, so the solution of this equation is -50. All right, back to the presentation. To finish off this section, we're going to look at some word problems. Everybody loves word problems. All right, here we go. Okay, writing word phrases as algebraic expressions. I've got all these written down on the tablet, so let's just go over there. Okay. Here we go. So the first example, this is a kind of important one. We're going to use this concept sometimes. A 5-foot piece of string is cut into 2 pieces. If one piece is X feet long, they want us to express the other length in terms of X. So let me draw a picture. I'm really good at drawing a picture of a piece of string. There you go. All right. This piece of string is 5 feet long. So what they're saying is, if you cut this string at some mystery point, like here, and this length is called X, what can I call this length over here? And I've had some really interesting conversations with classes, face-to-face classes, about this problem. All right, first thing you need to understand is that we are not necessarily cutting the string exactly in half. I could be cutting it anywhere, okay? So what might be helpful is if I make a little chart and show you first piece, second piece. Remember, the total is always 5. Okay. So if I did happen to cut it exactly in half, that would mean the first piece is 2.5 and the second piece is 2.5. However, what if I cut off a 1-foot piece? Then what would the second piece be? It would be 4, right? Remember, it has to add up to 5. And if the first piece was 3.2, what would the second piece be? It would be 1.8. And think about how you figured that out. You probably figured that out by doing a little subtraction problem. You didn't have to do the subtraction problem for these other ones, but notice that that pattern does hold up. Okay. All right, so this is the part where I point out to you that if the first piece is 2.5, then the second piece is 5 minus 2.5. If the first piece is 1, then the second piece is 5 minus 1. If the first piece is 3.2, then the second piece is 5 minus 3.2. So what if the first piece is x? The second piece would be 5 minus x, right? That is a huge concept in algebra. See the pattern? 2.5, 2.5, 1, 1, 3.2, 3.2. This is a little more fun to do in front of a face-to-face class because I've always been able to get somebody to say 5 minus x, and then I get very excited. All right, but that's all they're going for here. The second piece would be 5 minus x feet. Okay. So remember that concept. Whenever we need to use it again, I'll say, remember the string problem. All right, next example. Two angles are called complementary if their sum is 90 degrees. Okay, so complementary, oops, I just noticed a typo here. All right. Complementary angles look like this. Okay, they add up to 90 degrees. If one angle measures x degrees, they want us to write the measure of its complement, which is this angle here, in terms of x. So think about, where have you seen a problem like that before? Well, I could think about approaching it the same way I did the last problem. For example, if the first angle was 45 degrees, I want the two angles to add up to 90. That would make the second angle also 45 degrees. But if the first angle was 30 degrees, what would the second angle be? It would be 60 degrees, right? And if the first angle was 17.2 degrees, what would the second angle be? Well, now I need to figure that out. 90 minus 17.2 is 72.8, isn't it? Does this problem seem familiar? It's just like the string problem. We have two mystery numbers that we want to add up to a specific number. Okay, so when the first angle was 45, the second angle was 90 minus 45. And when the first angle was 30, the second angle was 90 minus 30. And when the first angle was 17.2, the second angle is 90 minus 17.2. So if the first angle is x, the second angle is 90 minus x. All right, so it's that same trick that we used in the string problem. All right, last example. This is a different kind of problem. If x is the first of 4 consecutive even integers, they want us to write their sum as an algebraic expression in x. So let's talk about, what do they mean by consecutive even integers? Can you think of an example of 4 consecutive even integers? Well, one example would be 2, 4, 6, 8, right? But that's not the only example. You could also have 14, 16, 18, 20, or you could have 80, 82, 84, 86. All right. So I think everybody knows what I mean by even. And what I mean by consecutive is we're not skipping any. So what if the first one of these was x? If you look at the pattern, in the other examples, notice to get from the first number to the second number, you are always adding 2. So the second number would be x plus 2. The third number would be x plus 4, right? And the fourth number would be x plus 6. Okay. So that's the first hurdle in this problem, is figuring out how to write the other 3 numbers. And now the easy part is we have to write their sum. So what is the sum of x, x plus 2, x plus 4, and x plus 6? Well, first of all, I don't really need those parentheses. I have a whole bunch of like terms. I have 1, 2, 3, 4 x's, which is 4x. And then I have 2 plus 4 is 6. 6 plus 6 is 12. So the answer they're looking for here is 4x plus 12. And that is going to do it for section 2.2. We will see you next time.